Okay.
Next to speak is Miko Herrero. Miko is in Germany and doing her PhD in Geomar Helmholtz Center on volcanism primarily, but ocean floor volcanism. Is that right, Miko?
Yes. Yes.
Okay, so we're ready to hear your presentation. May mga
Okay.
experts sa ocean floor din dito sa room. So
I know,
send
right?
your questions. Yeah. And also, JD, you can check the group chat. There are some questions to you already. Okay, take it away, Miko.
All right. Share. Okay. All right. So good morning, everyone, for those who are there in the morning. For my presentation, I want to talk to you guys about my experience when I was starting out with the PhD. So this is more of like a story rather than a scientific session. So I'm sorry about that, but I'll try to get into the science as well. So this is a story where I want to tell you that you don't really have to be an expert at first to be able to contribute to something remarkable, and that a fresh pair of eyes and a fresh brain is actually as valuable as having years of experience, especially when you're working in a team. So the title of my presentation is Rediscovering the Seafloor, the Search for Unexpected Volcanism. But first, did not work. Slide. Okay, but first an overview of what we do know about the seafloor. So right now, luckily, we do have a whole map of the seafloor. Like, people kept saying that the seafloor is so unmapped. There are so many dark areas that we don't know. But thanks to satellite altimetry, we do have a model of the seafloor. So we know the large-scale structures. We know where the plate boundaries are. We know where the big volcanoes are. We know where it's active. So if we're doing research, we know what to target and where to go to. And when we go there via our ships, we can do more detailed mapping, and we can do sampling and get to know more about the seafloor. But we have a good general overview of it. Yeah. But if you're a volcanologist who wants to study the seafloor, what you will target are the active sites, because the seafloor gets old and it gets covered with sediments pretty quickly, and you won't be able to see anything after a few million years. So you got to look at the active areas. So here we have a map where all the light blue dots are earthquake events, and all the triangles are known volcanoes. So we do know where to target. If you're a volcanologist, you know where to go. So for example, we can go along subduction zones, such as where the Philippines is. We can also go to where we have hot anomalous areas in the crust that we can call a hotspot, like in Hawaii. Or we can also go to where the plates are tearing apart and spreading and creating new ocean floor, such as along mid-ocean ridges, such as here in the mid-Atlantic. So yeah, you would notice that most of the activity is actually underwater. So the plus side is that you'll be at the frontier of discovery when you go there. But also the minus side is that it will take you one cruise at a time to actually discover things, and it'll take more time to share it to the world. So me, as a new PhD student, I actually came in not knowing anything about the seafloor, or I just know the very general things, like, yeah, where the plate boundaries are, where the big volcanoes are. But I came into this world with just volcanism, land volcanism, in my backpack. So I had to relearn everything. I had to look in articles, try to observe what they observed, try to do the methodologies that they did, and discover the seafloor as people have seen before. So first we start with large features that we can look at from afar, such as, this is the North Atlantic region, by the way. So here we have the mid-ocean ridge, and we can see these dots. These are seamounts, some old seamounts, and here are volcanic islands. So these are, some of those underwater are new seamounts. And here we have a lot of faults or transform faults. So we can see those large structures and we can describe them very well. And we look in closer, now we get this kind of map. Highlighted areas are the high resolution maps that were acquired with the ship. The darker parts are the satellite data, the maps created from satellite data. The high resolution maps can reach up to 100 meters, and the very low resolution can be even 1,000 meters in some areas in resolution. So I guess in this part, when you look at the details, we are still mostly blind in a way, because we always target those big, large features, and we always go there. As you can see here, this is the mid-ocean ridge, and you can see how much they have mapped in this area, because they want to go there, they want to study, and they map it in detail. And these lines over here, these are called transit maps. It's basically passive mapping. Like they turn on their mapping device as they go to their research site. So these are basically archive data that no one really looks at. Maybe someone was looking at the monitor while they were in the ship as the data was coming in. But otherwise, what is really processed is the target sites and not these transect lines. And for me, wanting to be challenged as a new PhD student, I said, okay, I'm going to study those transit lines. I'm going to look into those data because no one's ever written about them. No one's tried to look at them. So I want to have the opportunity to try to maybe see a pattern and whatnot. Maybe there's something, or maybe there's completely nothing. That's why it's not targeted, but who knows? No one can say no. So when we look at a map, a ship data really closely, we can derive at least two types of map from here. One is the bathymetry and one is the backscatter. So ship data, the way it acquires its data is through sonar, much like dolphins and much like whales. So your ship sits on top of the water and it sends down sound, and the sound will hit any surface. And the sound will either reflect back, and the ship will try to detect that sound. For bathymetry, that sound is translated as distance through time. So it's measuring the depth. It's translating it into depth or elevation. So this is like our topographic map, basically. For the backscatter, it measures the intensity of the sound that comes back. So imagine you have your ball, and you bounce it on really hard pavement. It'll bounce back really hard to you. As opposed to when you bounce your ball on sand or on sediment, it's not going to bounce back as hard. So from the ship, your sound hits hard surface, it'll come back high intensity. And in my map down here, high intensity is white, so these parts over here. And low intensity backscatter is dark. That means that that's where sound was absorbed and didn't really come back to the ship. And usually, high intensity sound would indicate hard rock, exposed rock. So along fault lines, along new volcanism, along mid-ocean ridges where you're creating new rock, it would all be high intensity signal or bright signal. But for most of the ocean floor that's covered with sediments, it's going to be dark because most of the sound has been absorbed and it doesn't go back to your ship. So that's why you can see some parts here are just basically gray or dark. But yes, so bright signal means hard surface, dense surface, or very reflective slope. So I have most of the transit data in the North Atlantic, and I look at it from coast to coast, trying to look for patterns. And here we have the bathymetry, here we have the backscatter, and I don't know, I was observing something weird, I guess. Like, I don't know what it is. It's just white blobs sitting on the ocean floor. I have no literature to try to find out what exactly it is. I can try to make assumptions that maybe it's precipitates that develops through time and hardens, so it's highly reflective, or maybe it's not, I don't know. For now, I mean, during this time, I'm just observing. I'm counting, I'm mapping, I'm observing. So we don't know what's going on. And one day, one of our postdocs, he comes to my supervisor. He just came from one of his cruise expeditions. And he said that he was watching the monitors in the ship, and he started seeing this white blob as they were going along transit. Like, it's not even their actual research site, it's just going along transit. And he was like, it's a white blob, I don't know what it is. And my supervisor doesn't know either, because I haven't shown him my data, actually, because I was still compiling all the information that I wanted to know. And then when I found that out, I was like, oh, white blobs? I've seen a lot of white blobs. I've actually mapped them out, and they're actually everywhere. So he was very surprised because it was something new. It was something unknown. And apparently I've been seeing it everywhere using the transit data that no one really looks at. So I was really excited. We were really excited to discover something new. So looking closely into the map, we find, we tried to do more observations just with the map. You can see here, for example, there are two pimples, two dots, and they look a lot like volcanoes. And then the white blob surrounds those volcanoes, and they sit ponded within the depression. So what kind of process on Earth can possibly do that without making it too complicated? And the only thing we can think of is volcanism. That's a volcano that erupted, created a lava flow that deposited within its depression or surrounding depression. And in this area, that was weird. We are on 20 million year old crust. It is quite far from the mid-ocean ridge, from the main active zone. It's quite far from any hotspot. There's no new hotspot or no actual heat anomaly in that area that we've looked for. So it was strange, because these are small-scale volcanism that's appearing out of nowhere, unexpected volcanism. So 6 months later, we were able to actually hitch a ride on one of the research expeditions with a biology group. And so they were crossing across the Atlantic and taking samples of water. And we have this target site here. This is our team. We're just 4 people. And we were tasked to take videos of the ocean floor. We were tasked to take samples of the ocean floor and to do some detailed mapping there. So this is our office system, which is basically a camera. You see the camera here attached to a rig. And it's basically something that you tow behind your ship, and it'll take the top view vision of your seafloor. And it's actually like bouncing up and down. So it's kind of dizzying to watch the video, but it's still pretty amazing because you're seeing the seafloor for the first time, or at least for me, it was my first time. It was quite amazing. So this is us sitting for at least 10 hours, just trying to take notes, trying to observe, and yeah, just being excited about what we're seeing. One of the most special things that we saw are these rock fragments and these pillow lavas. You can see they're very distinct shapes. And knowing that we are on 20 million year old crust, we're not supposed to see exposed rock, or not these kinds of exposed rocks. Usually there would be faulting, but there won't be actual young volcanism. So when we saw these, it's like, oh yes, absolutely, it's volcanoes. What is happening here? What is going on? So yeah, we were just watching the videos, and then well, some of the pillow lavas look very similar to human anatomies, which keeps the video a lot more interesting also. And then for the sake of the biologists, since we're just hitching a ride, we also need to give them data. So we try to time all the times when we see some fishes. There's not a lot of life, so there's not a lot of data for them, but there is life. There's fishes and there's some sessile organisms. You can see here it's attached to the rock. Some jellyfish passing by, of course. But most of the time, really, sitting watching the video, it's just mostly sediments, except for those exciting times when there's some pillow lavas. The one way that we sampled is using a gravity corer. It's basically a big pipe, hollow pipe, that has a weight on top that you drop onto the seafloor, and you hope that it'll stay vertical and punch through sediments and actually keep the sediments in its tube. So when you bring it up, you're hoping that the sediment will stay inside. And here, one of our cores actually got sediment, but we weren't so interested with the sediment. For this core, we actually hit rock. You can see here that the tip of the core was very dented, so it hit the rock really hard, and and the sediment deposition on top was very shallow. This is less than a meter of sediment on top. And for a 20 million year old crust in this area, you're supposed to have sediments. The sediments rate is 10 to 20 meters per million years. So definitely this surface is much, much less than a million years. So what is happening here? Why is there lava in this area or rock in this area? And then one of our cores, which is actually one of our most exciting moments as well, was able to sample these guys. These Oreo crumb looking things are glass shards. And glass shards are the best sample you can find for geochemical analysis because they're basically the purest geochemical sample of your rock, because it's very homogeneous. And what's special about this is that your glass shards, usually they're the first ones to turn into clay. They're the first ones to disappear and weather away. But here, they're very fresh, they're very shiny, like freshly smashed bottles. But these are very tiny. They're like 2 millimeters less in size. So they're very small and they should disappear really fast through time, but they did not. So that means that they're very young. Another way of sampling is by dredging. So this is basically a heavy basket with a netting underneath that you drag along your seafloor, hoping that you would catch rocks inside. Most of the time they turn out empty. We were able to get one small pillow, but it wasn't as wonderful as the glass shards that we got from the corer, which is fine. We also did a lot of mapping, a lot of detailed mapping in the area. We tried to get as much of the white blobs that we can, and we had fun with the names of the white blobs because back in 2007, Game of Thrones was still a good show. Not anymore though. But so we had fun. And after all that work, there's always time to relax in the ship. So here is us in a makeshift pool inside the ship because we're not allowed to swim outside of in the ocean, unfortunately. So the crew members made this pool and anyone can swim in it, which is fine. Back at home, I got the opportunity to sample the glass for their geochemistry. It was my first time using a microprobe and using an ICP-MS, a laser ablation, and it was really fun. And don't ask me about geochemistry, it's not my forte, but here's some graphs. So the red diamonds is our data, and this is just to show you how different they are from what normal seafloor volcanism geochemistry would be. So these white dots are from the mid-ocean ridge nearby, and these orange dots are from hotspots. And our data is not within that cluster. So that means that something different happened to them. They went through a different process before they came out as lava flows or as rocks on the surface of the seafloor. And it's not a typical type of volcanism that we would usually expect. So for most of my part, I just kept mapping all those transit data, and I see them everywhere. These yellow polygons are all those highly reflected areas, and they're everywhere. They're near old hotspots. They can be near mid-ocean ridges. They can be very far from mid-ocean ridges. They can be near subduction zones. They're just everywhere. They're small-scale volcanism, young volcanism that hasn't been studied very well. So for my part, I have this duty to tell people, like, why won't you go here? If you're looking for a place to spend your money on, why won't you go here and take samples, and maybe we'll find out more about the seafloor. But of course, that's not the case. There's more important science to be done that can contribute to society. And yes, this is more of for the love of science, getting to know the geology of our Earth more, getting to know what's actually going on with the seafloor. And also, so I was mainly studying in the North Atlantic, but whenever I get data, I also look at other areas of the world. So here, this is available data from when they were looking for the Malaysian Airlines airplane that crashed a few years ago. They made this available, and my professor immediately told me to try to look for white blobs there. So I did find one over here. It means that these white blobs are ubiquitous in any part of the ocean, not just in the North Atlantic. Oh yeah, so this is my part of rediscovering the seafloor, basically looking at data that nobody looked at before. And this is because I was new to this world, I didn't know anything, and it was my own curiosity that really pushed me to try to just look at things that other people aren't familiar with. And we ended up finding unexpected volcanism, and yeah, it was an amazing experience. But more so, overarching all kinds of sciences, being inexperienced in something shouldn't be treated as a hindrance, and it should be seen as more of an opportunity for a new set of eyes to look at things. So yeah, that's my presentation. Thank you very much.
Thank you, Miko. So paging Dr. Yumol to explain what those volcanisms are. So in summary, you found volcanism in the ocean floor, quite young, that's not related to mid-ocean ridges, nor is it hotspots or in subduction zones.
Yes.
That's pretty cool, and looks like you're having fun there, Miko.
It's pretty fun, yes.
Thanks, Miko. Quick shout out to Dr. Leo Armada and Dr. Lagmay is here. They're also in the Zoom meeting. Okay, moving on. Thanks, Miko, again.